Hey everyone, welcome to our intro workshop to data science. This is our third workshop in our workshop in our intro to software engineering series. My name is Jerry, and I have Keshvi with me here today, and we're going to be talking about data science.
All right, so just a quick overview of what we're covering today. We're going to start off by discussing what data science is and what the overall goal of data analysis is and why it's important. We're also going to go through the steps in the data science life cycle. And before we get into some basics, we're just going to go through all of that. We'll also talk about data cleaning and EDA, which are both important steps in the life cycle, and we'll get into that later, and we'll get into why they're important also. And then after that, we're going to talk about making predictions using machine learning and the difference between two types of predictive modeling problems, which is classification and regression. And then Jerry is going to finish it off with a demo. All right, so what is data science? Data science is generally a field of computer science that is specifically concerned with finding meaningful patterns in data sets using math and programming. I also like to think of it as the process of manipulating raw data to yield the answers that you're looking for. So when you're analyzing a data set, you usually start out with a specific question that you want to answer or a problem that you want to solve. And the end goal of data analysis is to gather meaningful insights and to make predictions about the data. So these insights and predictions can then be used to solve your business problem or your question. So just to reiterate, data science is really just about manipulating data in a way that will best reveal specific insights and allow you to make future predictions. It also encompasses the tasks of preparing data for processing and performing advanced data analysis. Okay, so now we're going to go over the data science life cycle. So the first step is called business understanding, and this step is essentially just about defining the business problem that you want to solve and the specific goal of your analysis. Usually you'll have like a client that wants you to make a certain prediction or wants a specific answer to a problem, and they want to use your predictions to solve that. So the next step is, after business understanding, is data understanding, and this just involves the collection and exploration of all of your available data. And all you're doing in this step is trying to identify what data is relevant to your business problem and what data will be helpful to your analysis. Okay, so next comes the data preparation stage. And this step involves data cleaning, which we'll get into in the next slide. But essentially, this step is about preparing your raw data for analysis and processing. And this step is important because your final model is only as good as your data, and your data needs to be clean. The next step in the life cycle is exploratory data analysis. And in this step, you're exploring your data, usually graphically with visual representations. And you're doing this with the goal of understanding and condensing your main characteristics in your data, which we'll also get into later. After EDA is data modeling, and this step involves choosing the appropriate type of model and which algorithms you want to implement. Then comes model evaluation, where we evaluate the model on whether it's ready to be deployed. And depending on how the model performs on new data, we may have to repeat the previous stages in this cycle until the model can achieve the right result. And finally, after your model passes evaluation, we get to model deployment, where we can actually deploy our model. And that's the final step in the data science lifecycle. Okay, so why is data science important? So we discussed earlier that data science is about extracting meaningful insights from raw data. Data science is important because it allows us to translate raw data into meaningful conclusions, and it even allows us to make predictions based off of these conclusions. This is especially important to businesses because businesses can analyze their user interactions and their user data to draw insights that will allow them to compete with other companies, make strategic business decisions, and make predictions about how a new change or product might be received. So in this way, raw data can be translated into tangible business value. Businesses might also use any analytic future predictions to decide how they can evolve to stay in the competition. And data analysts will often be hired by new companies who come to them with specific problems. For example, a business might want to predict the price of a commodity, and they might hire a data analyst to help them do that. So yeah, basically data science just allows us to easily understand trends from raw data, which is just a bunch of numbers, and it also guides business decision making, and it provides us with metrics, with quantifiable criteria, and it allows for insight into future behavior. And this is really, really important for businesses, especially. All right, so now we're going to get into data cleaning, which was basically just the data preparation stage of the data science lifecycle. And this is, in layman's terms, it's just the process of preparing a data set for analysis by removing or correcting outliers and errors in the raw data. So this step includes selecting which data is relevant and discarding any irrelevant data. It also includes merging data sets, cleaning them, making sure all entries are complete and uniformly formatted, just handling outliers, removing unwanted columns and features, and correcting any other kinds of errors in your raw data, because you need your data to be uniform and to make sense and to be complete in order for you to perform algorithms on it later and to analyze it later. And the purpose of this step is really just to help to maximize the dataset's generalizability. And generalizability of a dataset really just refers to a model's ability to adapt to new and unseen data. So this step's really important. It is very time consuming, but it's really important because it will determine whether your model will work on other datasets. All right, so now we're going to talk about EDA, or exploratory data analysis, and this is just an approach to analyzing data sets and summarizing their main characteristics via visual representations or visualization methods. So yeah, visualization methods just refers to like graphical representations like scatter plots or bar graphs. When we're talking about the characteristics of a data set, so for example, if you gather data from a group of people, then your raw data might have quantitative characteristics like age and weight. So we're talking about summarizing those attributes of your data in this step. So EDA really just helps data analysts to determine the best way to manipulate a data set to get the answers that they need. And it also makes it easier to discover patterns, spot anomalies, test hypotheses, and check assumptions. So also a really important step. All right, so now I'm going to hand it off to Jerry.
Yeah, for sure. And so one really important thing in data science is for us to sort of consider whether we want to be doing any sort of prediction. As often we have business needs in which we're trying to predict a certain either like a target amount of like audience or like a target audience to reach or a number of people that we're trying to sell a specific service to. So this is sort of where machine learning comes in. If you don't have much experience with machine learning, it's basically a mathematical framework for us to try to find a function to predict certain values. And we're going to be focusing on a specific subsegment of machine learning called supervised learning. And supervised learning mainly focuses on two categories, which are regression and classification. Regression and classification are similar in that you're both trying to use math to fit a function. You're trying to use math to fit a function to predict certain values. The difference comes in the fact that regression, you're often trying to predict continuous real values, such as like values on the real number line, whereas for classification, you might be trying to predict discrete values or classes, or maybe even categorical data. To go into an example of this, we can go through a general overview of supervised learning. So classification, if we consider the two classes with like the purple pluses and the green and the blue dots, these can be considered two pluses, and we can be using a model to predict whether something is of the kind of like the purple plus or the green or the blue dot. Whereas with regression, we might just be trying to, for each of these like dots, we're just trying to predict a specific, or just trying to predict a specific value that might lie close to it. Just a brief overview of unsupervised learning. Unsupervised learning has to do, or very often it has to do with clustering, and it has to do with data that isn't labeled. So if we're trying to find specific sort of, we're trying to find specific patterns in our data without having any prior information on labels for the data, unsupervised learning is sort of the machine learning process that would go through. Generally, in data science, we're going to be using a couple of different technologies. Python is a really popular technology to use in data science since it has a lot of really well built-in libraries and packages for you to use. So typically in Python, we'll be using libraries like NumPy, Pandas, sklearn, and TensorFlow, along with Matplotlib and Seaborn. So NumPy and Pandas are both data analysis and scientific computing tools and libraries. sklearn and TensorFlow both relate to machine learning, and Matplotlib and Seaborn are both visualization libraries, where Matplotlib is sort of the building block of all other visualization libraries in Python, and Seaborn is Seaborn is a more statistical exploratory data analysis type of visualization tool. Going into other technologies that you might use in data science, MapReduce and Hadoop are services that, or are software packages that we often use to prepare and process our data before we actually do data science. And SAS and Apache Spark are sort of distributed systems for data analysis and machine learning that often include implementations of a lot of the libraries we just talked about, and also things like MapReduce and Hadoop. And finally, Tableau is a visualization software written by Salesforce that is relatively popular in the data science field. And it's mainly used by data analysts in order to summarize findings of specific models or analysis cycles. So now we're going to be going through a quick demo of we're going to be going through a quick demo of a sample data set. And we're going to be using Jupyter Notebook, which is an IDE that you can actually run in your browser. And in Jupyter Notebook, we're going to be using Python to do our data analysis and also loading in our data into a data frame and doing machine learning on it. And we're going to be using a couple of libraries that I just mentioned. And while we're doing this, we're just going to have the two main goals of introducing what data cleaning and exploratory data analysis look like when we're actually writing code, and also showing a little bit about what model training and testing look like. So the cool thing about, so all the code in our demo is going to be in our GitHub it's going to be in our VandyHacks 2021 Spring Data repo. So the demo Jupyter Notebook is over here, and the data that we're going to be reading is this diabetes data upload CSV. So to start a Jupyter Notebook or an instance of Jupyter Notebook, it's relatively easy. We can just go into our command shell, and we can just type the keyword Jupyter Notebook. If we give it a second to run, it'll open up one of the localhost tree extensions, and this shows you basically all the folders and files on the main directory for your computer. So I'm going to be going into the GitHub directory and also into 2121 Spring One and going into the demo. All the code that we're going to be presenting for this demo has already been prepared. So I'm just going to be walking through some of the steps of what we're doing, and then also running the code and showing you guys what each code block is doing. So Jupyter Notebook is organized into cell blocks. So in each individual block, you can specify whether you want to be writing code or you want to be writing Markdown. And this allows you to basically comment your code in a really efficient way, and also give you a sort of, it gives you the ability to comment your code in a way that looks more like sort of generalizable text. If you guys want to access a specific library on your computer, all you have to do is install it onto your device first. And you can do that using pip install, and then you put the library name afterwards. So just to start off with our demo, what we first want to do in order to run any sort of analyses is import our libraries from our device into our specific instance of Jupyter. So in order to do that, we just use the import keyword and then we call the library. And sometimes we actually specify an alias for that library. So for NumPy, I'm going to be using NP. Like I mentioned before, NumPy is a scientific computing and data analysis, or a scientific computing and linear algebra library. Pandas is for data analysis. Matplotlib and Seaborn are both for plotting. So I can run this by either clicking the run icon, which will show me a little asterisk until it finishes running. Or I can simply press Control Enter, which will just run it a second time. So you can see that every time I run a cell block, it will just increment the counter. So next, what we want to do when we're actually working with data is be able to read our data into a data frame. A data frame is similar to a table in Pandas, and data frames allow us to hold tables and columns in feature columns, which have certain attributes, and also rows for us to analyze individual points of data. Pandas has a really nice built-in, Panda has a really nice built-in reader for CSV files for comma separated files, which are what CSVs are based off of. And we can actually just take PD, which is our alias for Pandas, and call read CSV, and then put the string name of our CSV file in for us to read it. So if I run this block, we'll read the CSV file into a data frame, but we actually won't be, it won't be printing anything out. We just know that our data frame is going to be called DF. If we actually want to take a look at what our data frame looks like, we can take a look at the top 5 entries of our data frame by calling df.head. .head basically allows us to take a look at the top X number of portions of our data frame. So if we take a look here, we can see that there's various different columns. I think there's actually 17 of them between age and class. One thing to notice is that class is basically a diagnosis of whether this person or the person with these specific data attributes has been diagnosed with positive or negative for diabetes. Also, Pandas data frames are zero index, just like pretty much everything else in Python. So this allows us to access individual rows using indexing, which is pretty nice. If we want to take a look at the last 5 entries of our table, or the last 5 row entries of our table, we just enter df.tail. And one cool thing we can do with df.tail and df.head is that we can actually pass parameters in. If we pass, say, like 10 into df.tail, what will happen is that it'll actually show us the last 10 rows of our data frame. So running that, we can see that we get 510 through 519, which are the last 10 entries. And with 519 here, 519 being our last index row for our data frame, we can also tell that there's 520 entries in our data set. But this is pretty much all we can learn from from our head and tail functions. So another quick way to get statistics on our data set is with the info function, and we can just call that directly on our data frame. And info basically gives us some nice information about the number of columns and the number of non-null and data types of each of our data entries. It's really important for us to keep track of our non-null counts or the non-null count of each column, because we actually can't do much with null values in a data frame. We certainly can't use it for analysis and prediction. So oftentimes when we see a certain number of null values, what we'll try to do is impute a specific value, or we'll just ignore it straight together and try to delete the row that those null values are in. And it's important for us to know the types of our data. It's important for us to know the types of our individual columns. You can see that the age is 64-bit integers, which makes sense since we have integers in our age. And everything else is an object, because I think strings are stored as objects in Pandas data frames. So we have 16 other columns of just strings. Also, if you guys have any questions during this demo, feel free to ask in the chat, and we'll be happy to we'll be happy to answer that as quickly as we can. Next up, we want to just get some, we want to get some more quick statistics on our data frame, and we can do this with the describe function. The describe function actually allows us to get some of the generalized statistics for all the numerical columns of our data frame. So if I call df.describe, I should be getting some statistics for our age column, since it's the only column that has, or it's the only feature column that has integer values. And if I run this, we can see that I get the number of entries in our age column, along with the mean, standard deviation, minimum, and a bunch of the quartiles and max. This is really important for us to keep in mind because when we're doing data cleaning, and especially trying to get rid of outliers, we want to make sure that anything past 3 standard deviations or a mean is excluded from the final version of our data frame, so that we can make sure that any models we train are generalizable and not affected too much by extreme values. So next up, now that we've learned a little bit more about our data set, we can do a little bit of our exploratory data analysis and actually work on some of the data cleaning. So here I'm going to be shifting over to Seaborn to do a couple of plots. So I'm first going to be doing a histogram plot and then a box plot. Seaborn has some pretty nice built-in functions in order to do that. I'm just going to be calling his plot at first, and the specific parameters that I pass into the function will be the column, and will be the column of the data frame that I'm using, age. And I'm going to be putting this thing called KDE equals true on. KDE stands for kernel density estimate, and it essentially draws a nice distribution on our histogram for us to see what the distribution of our data for our age looks like. And bins just refers to the number of intervals that we have for our histogram. Another cool thing that we can do in Jupyter Notebook is that if you press Shift Tab while you're inside the function signature, what will happen is that you'll get this nice printout of what all of the different function parameters can be. And you can specify any individual one of these in order to add extra parameters into our function. So you can see that the his plot, even though I'm only passing in 3 parameters right now, we can actually pass upwards of like 25 or 30 of them. And there's nice documentation within each of these to describe what each of the parameters are for. So I'm just going to run this code block really quick to show you guys what it outputs. And we'll see this nice plot of a histogram like we expected, and also this nice drawing of a distribution for our plot. So we can see that it's generally normally distributed, and we have a couple of outliers at the end where it looks like our 85 and 90 are a little bit separated from the rest of our data. One way that we can actually confirm whether these are outliers or not is by doing a box plot. Just a quick review on box plots. If you haven't seen them in a while, box plots basically give us, it plots out a box of our median or our mean, and also the various quartiles and the interquartile range for our data. So I can pretty much pass in the same, in Seaborn, pretty much all of the functions for plotting have the same function signatures. So you can pass in pretty much the same parameters in as well. So here I'm going to be passing in data for a X column and a Y column, since box plots will be looking you'll be plotting with, when you're plotting box plots, you'll be plotting both X and Y values. So here I want to plot class, which is a person's diagnosis for diabetes versus their age. And for the data frame that I'm going to be using, I'm going to specify that we use DF. So if we run this, we can see that there's 2 little dots outside of our 1.5 times our interquartile range on our box plot. So we actually pretty much confirmed that the 2 ages at 85 and 90 are outliers in our data set. So it's really important that we actually get rid of these before we move on to the rest of data cleaning or the rest of exploratory data analysis and actually train the model. So in order to get rid of these 2 points specifically, we know that both of these ages lie above 80. So what we can do is we can use bracket notation within pandas to get rid of them. So we can reset the value of DF to be the subset of DF such that the age column of DF is less than or equal to 80. And we just do that by putting this Boolean expression inside our DF bracket. And once we run this, we're not going to see an output. But if we add a cell below, and then we plot the same thing, then we should be able to see that there's no longer those 2 values. So the extreme points like 85 and 90 are no longer there in our data set. Now that we've gotten rid of these data points, the cool thing for us to do is actually take a look at the distribution of our age versus, take a look at our distribution of the age versus the class. So we can see the distribution of somebody's age versus whether they are positive or negative for diabetes. And in order to actually specify the class, all we have to do is turn on this thing called Q and then specify that it's equal to class. And again, we're going to be specifying that data is equal to df. One thing that you might notice is that the location of data equals df is different in these two function signatures. And that's because in Python, one really nice thing, or in pandas, one really nice thing is that as long as you specify the type of parameter that you're passing in, so if you're passing in data or you're passing in X, Y, or Q, and you're specifying that, then you can actually put those in whichever order you want. And pandas will, and Python will be able to read that and interpret it correctly. So once we run this, we can see that there's two plots. We're going to have the age distribution for negative diagnoses in orange, and the age and the diagnoses for positive diagnoses in blue. One quick thing that we can see from this is that people that test negative tend to be a little bit younger, but it still looks relative, and it looks like the distribution is bimodal, whereas the distribution for positive cases looks to be about normal. And also there tend to be more people that have diabetes in this data set than don't have diabetes in this data set. And that just comes from the fact that we see more higher peaks, and also the general distribution is higher for our positive cases. This is really important for us to keep a note of while we're doing model training and also model testing, because when we see something like this, we know that there's going to be class imbalance. Class imbalance is essentially the idea that when you have two classes or multiple classes that you're trying to predict, there might be one class that has more values than other classes, which often gives us, which often pushes us into the case where we can't use raw accuracy as a way to measure how our model is doing. And the reason why we can't do that is because if we have two classes, say A and B, and we have one class that has 99 values and another class that has one value, if we take a machine learning model, if we don't even use a machine learning model and we just write a function to return class A the first time, we'll have an accuracy of 99% on our data or like testing on our data set. But this won't be very well generalizable to other data sets because we're just going to be predicting A every single time. So next, I just want to be preparing our data a little bit for machine learning and also taking a look at the correlation between the various feature columns of our data set. So one way that I can do this is by creating dummy variables. I'm going to be typing in I'm going to be trying to visualize our table again. So we can see that there's 17 columns. There's one age column, which is numerical, and everything else is categorical. One thing that we can't do in machine learning is pass in words or strings and try to predict anything or try to come up with any sort of analyses, because machine learning models are based off or have mathematical backgrounds and can only be they can only be built off of numerical values. So in order for us to actually do analysis with our gender, polyuria, and all of our other feature columns, we have to convert everything in the rest of our data frame over to numerical values. And one way that we can do this is we can actually do it through one-hot encoding or creating indicator or dummy variables for each of these columns. One thing that, so we can notice that in each of these feature columns that are categorical, the data is binary. For gender, it's going to be male and female out of simplicity. For polyuria, it's going to be yes or no. And for all these other symptoms, they're going to be yes or no as well. And for class, it's going to be positive or negative. So we're working with binary data. So we can actually use a built-in function in pandas called pd.getDummies. And getDummies essentially allows us to return dummy variables for each of the columns that we're specifying and also the data frame that we're specifying as well. So notice that I'm putting in all of the columns that do not include our age, because we don't actually need to create dummy variables for our age since we already have that. We already have the age as sort of like a continuous stream of numbers. This last parameter that I'm passing in is drop first. Drop first essentially tells us that we're going to drop the first instance of the indicator variable that we're be creating. So one thing that getDummies does is that this function will return two indicator variables for each of our columns. It's going to return a gender male, and it's going to be ones and zeros, and there's going to be a gender female column returned for the gender as well. And it's going to be doing the same thing for polyuria, polydysphia, and all of the other feature columns that we have. And if this happens, then we'll have for each of these columns that we have in our data frame currently, we're going to have two columns in our new data frame that will be perfectly correlated with one another. And this is going to be really bad when we put it into a machine learning model, because generally ML models get really confused when the correlations between individual columns is really high. So if we run this code block, we won't see any output since we're just setting it equal to df. But if we if we call head on our df again, we can see that everything has been turned into dummy variables, so zeros and ones for our classes. And just keep in mind that the names of our columns have also been changed. So gender now has gender male since we dropped gender female. Polyuria is now polyuria yes since we dropped polyuria no. And our class has now been changed to class positive, and we've dropped class negative using our drop first parameter. So the last part of our really basic introduction to exploratory data analysis is that we want to take a look at the correlation coefficients between each of the feature columns. And I'm sure that you guys have heard about this before, but when we're trying to find which sort of vector or which variables are the best predictors of a specific output, we want to see which ones are most highly correlated with the output. Most highly correlated with the output in magnitude. So here we're just plt.figure is a matplotlib function that just allows us to specify the figure size, and heat map is a function that allows us to create a mapping of all the different feature columns that we toss in using a color-coded form. And this will make a little bit more sense once I actually print it out. For the data that we're going to be putting in here, we're going to be calling the core function on our data frame, which just generates the pairwise correlation coefficients between each of our data frame tables. CMAP just specifies the color scheme we're going to be using, and I really like full warm. And anno equals true just tells us to turn on the annotations, which means that it's going to be turning on the actual numerical values that each box is going to be associated with it. And here, tight layout just tells us that we don't want any overlap. So if I run this, it'll take a quick second to run since we're going to be calculating a lot of correlation coefficients between each of these feature columns. But once it plots out, you can see that there's a nice plot of, it's a nice heat map, and there's a nice legend for us to see what each of the correlation coefficients between each of the columns are. So we can see that the correlation between class positive and age is 0.93. And if we look for the highest value of, the column with the highest correlation to class positive, we can just do a quick scan and we see that 0.67, which is associated with polyuria, is the class or is the feature column that's most highly associated with our prediction class. So it's really important. It's really important for us to take a look at stuff like this, since oftentimes if we find that the correlation between two feature columns is really high, we might end up getting rid of one of our feature columns to avoid the issue I was talking about earlier. And also sometimes we don't want to overcomplicate our model too much. We just want a couple of different variables in. So we'll just identify the principal components of our model using correlation coefficient analysis. So moving on, we've done pretty much all the visualization and all of the data cleaning that we've wanted to so far. And what comes up next is essentially just training a ML model. As I mentioned earlier, sklearn is a machine learning model, or is a machine learning library that implements most of the basic machine learning models, from logistic regression to classification to basic neural networks. And we can import specific libraries and functions from sklearn in order to help us, to help us do our model training. So one thing that we have to do before we train our model is that we can't actually just toss in our entire data frame into our model. What we have to do is split it up into sort of deep independent variables that we're using to predict an output, and the dependent variable that we're trying to predict. So I just called our set of independent variables x and our dependent variable y. So for x, we just want all the feature columns to be, in our data frame, except for class positive, since class positive is the thing that we want to predict. And for y, we just want to select our class positive column. And we're going to be doing that by just using bracket notation in Python or in pandas. In our to generate our x data frame, we just have to drop one of the columns from our data frame, which is class positive. And we specify that the axis is equal to 1 in order to tell the drop function that we want to drop a column. If we put that axis is equal to 0, or if we eliminated this altogether, then what we would then pandas would automatically assume that we want to drop a row instead. So you want to make sure that we specify that that axis is equal to 1. We're going to run this and we're not going to generate any output. But if we look at the columns of X, we can see that all the columns from our data frame are there except for class, or except for I think class positive. And if we just call the same function on df, which is our complete data frame, we'll see that class positive is there. So there will be obesity yes at the end, and then class positive right after that. And for our X column or our X data frame, that class positive is no longer there, which means that we've properly generated a correct set of X independent variable matrix. So the next thing that we want to do when we're training our machine learning model is to create training and testing data. The reason for this being is that when we have to use data in order to train our model, but after we train our model, we want to be able to test on how well it classifies. So we'll usually take our initial data set and we'll split it into training and testing data. And the way that we do this is simply by using the train test split function that we imported from the model selection library. And we're gonna be passing in our X independent variables, our prediction column, and our test size and random state. Our test size just tells us what fraction of our testing set, or what fraction of our data set we want to use for testing. And random state is basically a C generator that allows you to get the same value. It allows you to get the same value if you're running the code in conjunction with me. Note that there's 4 different variables that I'm putting on the left here. Train test split actually returns a 4 tuple. The first variable being X train, which is the X data relating that we're gonna be training on. X test, which is the testing data that we're gonna be using to predict. Y train, which is the associated Y labels for our class that we're going to be training on, and then Y test, which are the true values of true values of classification for X test that we're going to be using as testing values against our predictions. So the next thing that we want to do is basically instantiate a version of a regression model and use it to do predictions. One cool thing about sklearn is that all of the models in machine learning that are in this package they're implemented in an object-oriented way. And this kind of allows us to create instances of our models. So what I can do is actually, for this logistic regression that I imported earlier, I can take reg, or I'll take a variable name and I'll call it reg, and I'll actually just create an instance of logistic regression. And I'm going to be passing in a function parameter called max iter and set that equal to 150. This just means that we're going to be doing at most 150 iterations of gradient descent before we specify at which value we're going to be stopping at. If you're interested in some of the other parameters that can be passed in, you can take a look at some of the you can take a look at some of the possible function parameters. It might not really make sense what some of these things do, because it does require a little bit of intuition and understanding of how machine learning models actually work, and what and on concepts like regularization and penalty for us to actually make use of some of these other parameters. So for now, I'm just going to be putting together a really bare bones version of our logistic regression model. And just to introduce logistic regression is a type of classification model. And it essentially predicts the probability for which a set of it predicts the probability for which a row of our X data table is going to be positive or negative for or it's going to be positive or negative for our actual diagnoses. And if the positive probability is over 0.5, then we're going to output a 1. And if it's less than 0.5, we're going to be outputting a 0. Training our actual model is relatively simple for a sklearn model. All we have to do is call the fit function on reg, and we're going to be fitting it on our X training data and our Y training data. After we've done that, we can create a specific prediction, and by calling the predict function on reg, and we're just going to be using predict on our X test values to generate a set of predictions that will later be comparing to our Y test values. So if I run this, I'm not going to have any sort of output, but I accidentally deleted that. But if I print this out, then I can see the values that I'm predicting. So I'm going to be predicting a bunch of a 0, a 1, a bunch of zeros, a bunch of ones, more zeros and ones. And this actually makes sense because after we made dummy variables with our individual columns in our data frame, our class, or the specific class that we're predicting, is now only zeros and ones. So now that we've created a prediction set or a set of predictions for our testing set, the next thing that we want to do is sanity check this testing set, or sanity check our prediction by comparing it to specific testing metrics. So we're going to be importing two different reports from our metrics library in sklearn. And these are called the classification report and confusion matrix. So once I print these two out, I can call the classification report and confusion matrix on our X test and our pred, our Y test and our pred. Y test just being the true Y values that we want to predict, and pred being our predictions of those true Y values. So once we print this out, we see that the classification report is actually just a really nice tabulated, table of individual statistics and based off of each of the prediction values. And our confusion matrix doesn't have any nice labels, but essentially what it does is it gives us a nice gives us a total of the number of true positives, false positives, true negatives, and false negatives in our data set. So the true positives is going to be the 1, 1 entry of this matrix. The true negatives is going to be the 2, 2 entry, and I believe the 2, 1 entry is going to be the false positives, and the 1, 2 entry is going to be the false negatives. And going back into our classification report, we have a bunch of different statistics that we like to look at. I mentioned earlier that accuracy is generally not a very good indicator of how well your model is doing for classification, due to the fact that we might have some sort of class imbalance. So the fact that this is doing 97%, or this thing is getting 97% accuracy, is not something that we should actually be super happy about. Instead, we should be looking at precision and recall. And precision and recall are basically are measures of the number of true positives and true negatives versus other sorts of metrics within our classification model. And these can be calculated with respect to negatives, negatives and positives for diabetes diagnoses within our data set. F1 score is an indicator of our, F1 score is basically a combination of our precision and our recall. Basically what we want to have is our precision and our recall both be very high, because precision and recall individually are important metrics, but if one of them individually is very small, then this tells us that our model is not very well rounded out, because we might be producing more false positives or more false negatives than we're hoping to do. So usually we try to find a nice, usually when we're testing out models, we try to find a nice sort of middle ground between our precision and our recall through our F1 score. Here, our F1 score is 96%, or 0.96 and 0.97 respectively. So that's actually pretty good. And by pretty good, I'm just basing it off of some of my past experience in data science. Usually what you want to do when you're comparing classification results or regression results is that you want to be comparing it to other models, because usually you don't there's not going to be a good number sense for like what is considered good precision or what's considered a good recall for a specific data set, since oftentimes in data science people are going to be working on data sets that they've never seen before. So what we'll often try to do is we'll try to test out some of these very simple classification or regression models on a data set, and then we might move to some more complex models, or we might move to some of the more complex models, and we can see how the performance of the model with respect to our precision and recall change, and also how much resources these more complex versus these more simple models will eat up. So below, I have some code for other types of models or other types of classification models that we can use for this problem. First being the decision tree and also the random forest. Decision tree is essentially a classifier that uses binary trees, or even trees with any number of branches in order to do predictions. And random forests are ensembles of independent decision trees, which you bootstrap together and kind of average out in order to get a better generalizable result. Additionally, k-nearest neighbors is a k-nearest neighbors is a classification model in which we take a look at our data by pushing our data into some n-dimensional space, and we look at the distance between each individual data point and our point that we're trying to predict the output for. And based off of the k-nearest neighbors of that of our testing value that we want to look at in n-dimensional space, we try to predict off of those. So that pretty much brings us to the end of the demo. I'm not going to be running any of the code from the decision tree random forest or the k-nearest neighbors classifiers, since I'm just going to be doing the same thing for the most part. I'm going to be calling, or I'm going to be initializing instances of these functions or these models. Then I'm going to be fitting and predicting. And then afterwards, I'm just going to be printing out the classification results again. So this brings us to the end of the model, our demo. And I just want to remind everybody of what we've done so far. In this demo, we've gone through how to import specific libraries, how to load a data set, and when we're working with a specific data set, how to clean the data, explore it, and also train a specific type of machine learning model called a logistic regression on it. Additionally, we also worked on ways to split our data into training and testing sets, and also how to clean it up, especially for the purpose of machine learning. And finally, we talked about machine learning testing, where we can test our results using tools like the classification report and the confusion matrix. And I just want to reiterate again that the testing that we've done and the sort of data cleaning that we've done for the purposes of this demo have all been for the sake of classification. We're trying to predict whether a person with certain attributes has diabetes or not. And when we're working in the case of regression, we're trying to predict like a real value, like we're approximating a function, or we're trying to find maybe the relationship between somebody's age and their height. We're not going to be having these binary output values. And instead, we're going to be trying to output something that is real valued and also continuous. If you guys are interested in looking at the code that we went over just now, all you have to do is come over to the GitHub, click demo.ipynb, and it should load this up into a nice Jupyter, a viewable file. You can actually clone this repo. I think it's public, and you can run it yourself and also run these additional code blocks down below. And if you're interested in looking a little at the diabetes CSV file a little bit closer, you can actually see that it looks relatively similar to our data frame, except that it's no longer zero indexed. Yeah, that pretty much brings us to the end of our demo. So we can go back to the screen share for our slideshow. Just wrapping up our presentation, data science is a super applicable subfield of computer science where we're often trying to find analytics, we're trying to extract really useful analytics and signal from a specific data. And sometimes we're even trying to use machine learning to either do prediction or even trying to find the most important predictors of specific factors within our data. As we saw earlier, the data that we were working with in our demo is actually pretty convoluted. We have a bunch of columns that only have categorical data like yeses and nos. And what we were able to do with some pretty simple data science techniques were to convert them into numerical values and then actually create a correlation plot and train machine learning model on this data in order to give us some better analytics of what's actually going on within a data set. This is a really useful skill since very oftentimes when we're working in data science or we're working with big data in today's world, we're going to have really complicated data that we're not really going to understand. And as data becomes more complicated and data starts being generated at a higher velocity, it's really important for people with data science backgrounds, or it's more important for people to have data science backgrounds if they're going to fields like software engineering or just tech in general. I talked a little bit about vectors, matrices, and linear algebra in our presentation or in our demo. And this is due to the fact that a lot of data science and especially machine learning is built upon statistics and linear algebra. So very oftentimes we'll be using statistical and visualization. We'll be using statistical methods in order to train data, in order to learn data for a model, and we'll be using specific visualization techniques to see what to sort of get an understanding of what our data is trying to tell us. And this will really help us in extracting these analytics and potentially helping us make informed business decisions later. So if you guys want to see a link to the GitHub repository, we've linked it down below. But this brings us to an end of our workshop. We just want to thank you again for attending today. It is a Tuesday night, so I'm sure that everybody has a lot of stuff to be working on as well. If you guys are interested in giving us feedback, we have a feedback link in the on the screen, and we'll also be dropping that in the chat shortly. And if you have any questions, feel free to stick around and we'll be happy to answer those as well. Okay, cool. If there's no questions, then I guess this is pretty much the end of our presentation, or it's pretty much the end of our workshop. Thanks to everybody again for coming, and I hope you guys have a nice rest of the week.